Hello, my name is Chen Griner, and our paper is called On the Complexity of Traffic Traces and Implications. This is a joint work with Chen Avin from Ben Gurion, Manya Gubadi from MIT, and Stefan Schmidt from the University of Vienna. Um, Let me start with the main question that we try to answer in this paper. How to define, categorize, and quantify the structure inside the traffic traces from different networks. To answer this, we use information theory and present trace complexity and the complexity map, which you can see here. In this example of the complexity map, we show traces from a Facebook data center, a high-power computing app, and a machine learning application. We believe that understanding the structure found inside the traffic traces and network traffic will help us design better networks in the future. So what is structure? Can we take an intuitive approach? Here we see traffic metrics from a Facebook data center. And we can ask, can we see some patterns or structure in this traffic metrics? Well, the answer to this is yes. We can see that there is this lighter colored region in the bottom left corner of the metrics, and we can see some darker colored regions in the left and right corners of the metrics. And so this metric does show some clear patterns. What about the network during time? Well, we see that the load on the network, which is represented by this graph, changes through time, and some of the regions are more lightly colored than the others, as we can see here. We then are able to divide this structure into two main parts. The two types that we explore in this paper, the two types of structure, are called temporal and non-temporal structure. Temporal structure is represented by the order of events, and non-temporal structure is more represented by the frequency of events. So let us look into the non-temporal structure first. Here we have a traffic matrix from a distributed machine learning application from a 4x4 network of 4 GPUs. Each source and destination GPU is denoted by a different color, and the height of each column in this traffic matrix denotes the amount of traffic between these two pairs. So can we see some structure in this matrix? Well, here it's harder to define, the structure is less clear, but a nice way to show the structure is looking at a traffic matrix that contains no structure. In this case, we chose the uniform traffic matrix to show a traffic matrix that doesn't contain any structure at all. All of the pairs communicate with each other in the same exact rate. So we can see that in the uniform matrix, indeed, all of the columns are about the same height, and there is no difference between pairs of destinations. So we can clearly see that the real matrix is quite different than the uniform random matrix. What about temporal structure? As we said, we also have temporal structure as well as non-temporal structure. So we can take a look at the trace that generated this traffic matrix that we saw before. Here in this timeline trace, we can see each pair colored in the same way that they were colored in the traffic matrix. And each line here represents a single communication event between each two pairs. So we can see that, for example, the red pair appears more frequently in the beginning of a trace, and it also appears as long bursts of traffic. Again, we can ask whether does this trace show any temporal structure. And to do that, we again ask how would a random trace look like. And here we have this IID trace where each message or each communication is independent from the other events. And it seems that all of the events here are uniformly distributed throughout the trace. So this is indeed quite different than the real network trace. However, this trace is just a permutation of the first one, and they are both eventually generate the same exact traffic metrics. So we know that the traffic metrics doesn't tell all of the story. So how do we measure structure in a more meaningful way and not just in an intuitive way? In our paper, we take an information theoretic perspective. That is, we use tools from information theory to measure structure. The first tool is called entropy or entropy rate, which is known as a measure of randomness of an information source. The lower the entropy, the more predictable the information source is going to be, or in our case, the network traffic is going to be more predictable. And the more predictable it is, it would also have more structure. And traffic with more structure is what we call less complex structure. Another tool that we are using is compression, which offers a way to estimate the entropy of some information source. But then the question arises, how do we combine these two tools in order to measure the traffic? So how do we represent the traffic? In our paper, we represent the traffic as a simplified network trace. This is just a table with two columns, a source column and a destination column. Each line contains a source IP and a destination IP. And these in the lines are ordered through time as in the same order that they appear in the traffic. This is, of course, a simplified trace which doesn't contain any information about time or payload or protocol or port, etc. So how do we take this simplified trace and use it to measure traffic complexity? So we measure traffic complexity with two steps. The first step is randomization. We take the trace and we sequentially randomize different aspects of the trace in order to remove certain parts of the structure from the trace. And this allows us to measure specific types of structure. The next step is compression. We compress the randomized traces, and we then are able to compare the size of this trace to find what is the trace complexity found inside of the network traffic that is represented in this trace. So what do we mean by randomization? We start with this trace, and this is the original trace. It contains both temporal, here represented by the gradient of the colors in the trace, and non-temporal, here represented by the fact that the yellow rectangles only appear in the source column, and the blue rectangles only appearing in the destination column. So we take this original trace, and we modify it slightly, and we create a permutation of the trace where all of the rows have been reordered randomly, uniformly. And as you can see, the gradient of the colors has now disappeared, but which is the temporal structure, and the non-temporal structure represented by the colors has remained the same. So this is a trace that contains the same temporal, non-temporal structure, but all of the temporal structure has now been removed. For the next step, we take the same list of source and destination nodes. However, we uniformly sample them to create a uniform trace. This trace now has neither temporal structure, as you can see there is no gradient, and neither it has any non-temporal structure, which is represented by the fact that you have blue and yellow rectangles anywhere in the trace. So we now have removed all of the structure as well as the non-temporal structure. And as a general rule, we know that since we only introduce more randomness, we introduce more entropy into each trace, the complexity of each trace is only increasing. So for the next step, we have compression. After randomization, we take each trace and we compress it individually using some common compression algorithms such as Lempel-Ziv. And after compression, the sizes of the compressed traces are again ordered by the complexity, since compression is related to entropy and complexity. How do we take these compressed traces and define trace complexity using these traces? So let us talk about the formal definitions of complexity. Let us assume that C of sigma is the size of a compressed trace sigma. We define total complexity of being the size of a compressed non-randomized trace to the size of the uniform trace. Essentially, the ratio of a trace which contains no structure to a trace that contains all of the structure. We then can also define temporal complexity. This is the ratio of a trace which contains all of the structure to a trace, to a raw randomized trace, which contains only non-temporal structure, which gives us the temporal complexity. And finally, the non-temporal complexity, here it is defined as the ratio of the raw randomized trace to the uniform trace. Again, since the ratio of these the size of these randomized traces is only increasing, the complexity is found in the range of 0 to 1, and it is normalized to this range essentially. So how do we map trace complexity once we now have a way of calculating it? We use the complexity map. So the complexity map is essentially a 2D plane from 0 to 1 in each axis. The x-axis represents the temporal complexity, and the y-axis represents non-temporal complexity. And as a general rule of thumb, the closer we are to the axis origin, the less complex we are. And the closer we are to the edge of the axis, the more complex the trace is going to be. For example, in this edge, the coordinate 1, 1, we have a maximally complex trace. So let us look at 4 edge cases for the complexity map. The 4 edge cases are, we have uniform traffic, which is a traffic which lacks any type of structure and it has maximum entropy. It appears in the coordinate 1, 1 at the edge of the complexity map. And here is represented by this completely random uniform trace. The next type is bursty traffic. Here, all of the pairs appear with the same frequency with a uniform order. However, they appear in long bursts of communication, and therefore they are very dependent on each other. So this has a lot of temporal structure and therefore appears somewhere closer to the edge of the map on the x-axis. The next type is skewed traffic. Here, all of the nodes appear with different types of frequency, and therefore it is skewed, but they are evenly distributed, and there is no temporal correlation whatsoever between the different pairs. The last case is traffic which is both skewed and bursty, here represented by the machine learning trace. This is where we expect most traffic to be. It is somewhat skewed and somewhat bursty. But can we ask where the machine learning trace is actually going to appear when looking on the map? And to do that, we will look at the results of our work. So we start by looking at the results from the machine learning application, here represented by this yellow circle. And as we expected, the machine learning contains both temporal and non-temporal structure. It therefore appears somewhere in the middle of the map and not along one of the edges. And this result is not surprising. And what about the other results? We also have results from Facebook. This is a result from a Facebook database cluster, from a web server cluster, and from a Hadoop cluster. All of these show different levels of complexity, but as a general rule, they show more temporal complexity and less non-temporal complexity. Unlike these, the prefabric, which comes from a simulation, shows a greater degree of non-temporal complexity with a smaller degree of temporal complexity, quite unlike the Facebook traces. The high power computing traces show a similar profile to the machine learning, where they contain similar amounts of temporal and non-temporal complexity. And more interesting insights can be found in our paper. So what can we expect to learn from trace complexity? First, we expect that much as low entropy means better performing compression algorithms, we hope that low complexity would mean better optimization opportunities for different networks. We hope that complexity could be used to identify different structures and different patterns inside network traffic that will enable us to understand network traffic better. Further, we hope that trace complexity could be one of the measures that is used to identify different networks and could be used to see how much replicated traffic from a simulation is close to the real traffic from a real data center, for example. And since traffic could be quite similar in certain respects, such as the traffic metrics, but could be really dissimilar when we talk about the structure inside of this traffic. And of course, we offer more insight in this, including a traffic simulator inside of the paper. So for future work, we plan to test traces that have more different types of metadata inside of them, not just the IPs, but also the inter-array times, the ports, and payload. We hope to find other dimensions of complexity, some of which are already presented in the paper. We hope to see some practical implementation of complexity in the design of online algorithms that control different networks. And we have constructed a website which is called selfadjusting.net, which contains all of the traces that we used in this paper. And we invite the community to contribute further to this website. So thank you for listening, and that's all.